Yeah, so for the afternoon session, I want to give you a little bit of an intro to machine learning and scikit-learn. So scikit-learn is a project that's been going for about 4 years, and essentially the goal of it is to have a collection of really well implemented machine learning algorithms in Python. And scikit-learn strives to have a really clean and well-documented API so that, for example, if you learn how to use one machine learning algorithm, if you figure out how to apply one algorithm to your data, you can very easily drop in another algorithm and try that one out on your data and see how things go. So as soon as my computer is set up, we'll dive into this. I have a nice intro slide with the URL where you can go to download things. It's beautiful. You should see it. All right, so that should pop up. Yeah, so you can go here. I have my materials on GitHub. Like the previous presentations, they're in the form of IPython notebooks. So you can grab those. And basically, as you type that in and find those materials, I'll tell you a little bit about what my goal is for this afternoon. We have about with the break, we have about 2 hours to go through this stuff. And what I'm hoping to do here is, number one, give you a little bit of an intro to what machine learning is and how you should think about, how you should wrap your mind around what sort of problems machine learning is going to solve. And along the way, what I want to do is show you how the scikit-learn API works for applying these machine learning algorithms. And I'm going to have a couple example data sets and a couple little places where you can take a few minutes to try some code yourself. But for the most part, I want to give you the tools and the background so that you can take these machine learning applications in scikit-learn and apply them to your own data sets that you have. So if you follow this link here, you should find my GitHub scikit-learn tutorial page. And if you want to just follow along without actually running any of the code, you can click on the notebooks and click on any one of these, and GitHub will render a static version here. If you actually want to run the code and try out the examples yourself, I'd suggest either cloning the repository with this address, if you know how to use Git, if you're familiar with that, or you can click the download zip here to get a zip file of all the content. So once you have the content downloaded and you've loaded up the notebook, you should see a page kind of like this. And the dependencies are NumPy and SciPy, IPython, and then the scikit-learn package. So you can install scikit-learn if you have Conda. You can do Conda install scikit-learn. Yeah, if you installed Anaconda, you should have all those dependencies already. Yeah, and you can see that, oh, it's asking me if I want to update. I'm not going to update live right now. We'll do no. Okay, so let's click on the preliminaries here, the first notebook. And like I said, I want to, I'm gonna clear this output. The goals of this tutorial, I want to introduce the basics of machine learning, so the way that you can think about machine learning and what problems it solves, and introduce the syntax of scikit-learn so you can make use of these tools in order to do this. So this preliminaries, this just has some information about dependencies and things like that and checking your installation. So I'll skip over that, and if you have any issues with these dependencies, you can raise your hand, and a couple folks are around to help you out. But for the sake of time, I'm going to move on to this next piece. So this machine learning intro, part 2. So the goal here, I want to give you a definition of machine learning. I want to talk about how we represent data when we're working in scikit-learn. And I want to do a brief introduction to the scikit-learn API before we dig a little bit deeper later. So I told you about the scikit-learn package. But what is machine learning? So machine learning is not as complicated as it sounds. It's basically a way of specifying a model that a computer can fit to data so that it can make predictions about new data. And we'll see some examples of this. And the funny thing about this is that it seems really, really simple, but if you start applying this to more and more complicated data sets and more complicated models, you can do some really sophisticated things, as you'll see. So I'm going to start by running this matplotlib inline call, which will allow us to view our plots inline. I also this is what I tend to do with my own code. I import Seaborn and run seaborn.set. You can comment this out if you don't have Seaborn installed, but this just gives you a slightly nicer plotting defaults. I want to clear all output again. So as an example of a machine learning problem, this is a simple example right here. So let's say you have a collection of red points and blue points, two-dimensional data. You plot them out there, and you want to create an algorithm that will automatically tell you whether any new point that arrives that lands on this space is going to be labeled red or blue. What you can do is you can draw some sort of line that separates them, right? By hand, you might draw that line that we put right there. And now you can say that any point that lands above that line, when you have a new sample, is labeled blue, and any point that lies below that is labeled red. So this seems really, really simple, right? And this data and these labels could be anything. These could be, for example, features of your users of your website, and the blue points are ones that stick around and click on the next link, and the red points are the ones that leave and you never see them again. And you have some data features that tell you about them. So this is a simple classification problem. And it might seem really trivial, but you can imagine it as you have more and more features. If you have, instead of 2 features about each point, if you have 1 million observations or 1 billion observations or a large number, it becomes much, much harder to draw something like this by hand. And what a classification algorithm does is it tries to draw a boundary in your data like this so that you can label things blue or red, or you can label users that leave or users that stay, and you can start to predict about things. So one thing I want to point out is that I actually have the source code for this right here. This wasn't just, where did it go? Right there. Oh yeah, I actually have the source code. So I imported this from this Fig code that's as part of the repository. So this isn't just a toy image that I generated. This is an actual machine learning model that's computed with scikit-learn, and you can jump into the source code and see that if you'd like. So this is an example of a classification task. And another really simple machine learning task that you might be familiar with is fitting a line to data. So in this case, we have 2 observations of each data point. We have X data and Y data. And what we want to do is we want to use the X value to predict the Y value. So for example, this might be something like you know all the features of a house that's on the market, and you want to predict what cost it, what it'll sell for. And so a regression task is different from a classification task in that we're trying to predict a real valued thing, a continuous valued quantity. So here, given the X data, we're trying to predict the Y data. We have all these blue point samples here. And what we can do in this really simple model is just draw a line so that if, say, we find an X value of 15, we can guess that the Y value will be somewhere around 9. And that's what that line tells us. It's a model that tells us the relationship between the X and the Y. And again, this might seem really simple, but this is a basic machine learning model. We're taking data, we're taking input data. We're building a model based on that input data and some assumptions. Here our assumptions are that a line fits the data. And then given some new data where we don't know the Y value, we can predict what that Y value might be. And it seems simple in 2 dimensions, but if you start thinking about many, many dimensions, if you have thousands or hundreds of thousands of attributes, that you're measuring about a house, the number of rooms, the square footage, how old it is, what neighborhood it's in, what houses nearby have sold for. All of a sudden, this sort of regression problem becomes difficult to do by hand. But the machine learning algorithms that are implemented in scikit-learn and elsewhere can actually handle all that data and do this sort of prediction. So those are some simple, quick examples of what machine learning models look like. And like I said, it's kind of deceptively simple. It's something that you might think you can do by hand, but as it scales up, it becomes more difficult. So the question is, how do you start using this sort of model on your own data? And the first thing we need to know in order to use this in scikit-learn is to know how scikit-learn represents its data internally. And in general, scikit-learn data is stored in the form of a two-dimensional matrix. And this can actually be a pandas data frame, or it can be a NumPy array. And essentially, what the matrix is it's 2 dimensions where each row of the matrix represents a sample. So in our previous example, each row of the matrix would represent one house. So you have one house that's sold for a certain amount, another house that's sold for another amount. And the columns of the matrix, each column is associated with some observation you have of that. So column 1 might be the number of rooms in the house. Column 2 might be the number of bathrooms, et cetera. And once you have that two-dimensional matrix, you can feed that into the machine learning algorithms and go from there. So let's take a quick look at an example. We saw earlier in the bokeh tutorial, we briefly saw this iris data set. Was it bokeh or was it earlier? I can't remember. So this iris data set is a classic one that's used in statistics and machine learning that is used as an example because it's kind of easy to wrap your head around, and it's small, a few hundred features. So you got to imagine that you're a botanist and you're out in the field and you're taking a look at irises, and there are these certain species of irises that are out in the field and you're interested in looking at. And you observe these irises and you think to yourself, we can write a computer program that will determine the species of these irises. So what you need in order to automatically determine the species of these irises with a computer program, you need to first decide what the features are going to be. So remember, the features are something that you measure for each individual iris, and it's the same measurement that you make for each one. So looking at these different irises here, here's a setosa, here's a versicolor, here's a virginica species, 3 different species. What are some features that you might measure for these? Anyone have thoughts? Yeah? Yeah, length of the petals would be a good one. So the petals are these big guys right here. So you could go to each flower and measure the length with a ruler. What other features might you see? Yeah. Yeah, like the ratio between the width and the height, or some sort of aspect ratio of the flower, right? Sorry? Number of petals, yeah. So you could get the number. In the case of irises, they all have 3. So, but distinguishing between irises and other flowers, that would be a good one. Yeah. So you guys are getting the idea. You basically figure out what features you might measure that would be meaningful. So this is where your own domain expertise comes in. If you just came out here and started measuring random things, you probably wouldn't get a very good classification. But if you know a little bit about irises and you measure things that you have intuition will give you good information about them, then you can do a better job. So that's one important thing to know about machine learning is it's good to have some sort of domain intuition that you can apply to the problems that you're doing. Another thing that sometimes people suggest here is you might actually use just the images themselves. You could use, for example, this upper left pixel value as a data point, and then the pixel value next to it as a data point, and the next pixel value. So if you have 1,000 by 1,000 pixels, then you have 1,000,000 data points that you can use to help classify this iris. And there are machine learning pipelines that can do that sort of image-based classification. It tends to be really, really difficult, though, and you usually need need a lot of data in order to do that sort of thing. So these engineered features where you do things like measure the length of the petals are usually easier. So in this case, with the iris data, what's in this classic data set is exactly what a few of you suggested: the sepal length in centimeters, sepal width, petal length, and petal width. So it gives you an idea of the aspect ratio of the different components. It gives you an idea of the widths. And the target classes that are in this data set are these 3 species. So we can start by, in scikit-learn, this iris data set is built into the library. So we can load it this way, and we can take a look at the data set. And we see that there's, in the iris data set, we have a description, we have a target, feature names, we have the data. So let's look at this. We have, if we look at the data, I told you that the data should be in the shape of a 2-dimensional matrix. So this is, in this case, it's 150 by 4. So you can picture this long, tall matrix. And if we, actually, I'll take a look at the data right here, iris.data. You can see that it's this long, tall matrix, 150 rows by 4 columns. So each of these rows here is a single iris that was measured, and each of the columns is one of the measurements that was made. So your data is organized in this nice uniform manner in a 2-dimensional matrix. And then the other thing that we need to know is we need to know about the target. We need to know about the value that we're trying to predict. So when we're training a classifier, the target is, in this case, it's a discrete value where 0 represents one species, 1 represents the next, and 2 represents the next. So using this iris data in this form, we can then plug this into the machine learning framework in scikit-learn, and we'll see that. And the last thing, if you're curious what this 0, 1, and 2 means, we look at the target names attribute, and it tells us that 0 is Setosa, 1 is versicolor, 2 is virginica. So one of the first things, when I come across a data set like this, I find one of the first things that's useful to do is to plot the data. And here's an example of a plot of this data. We have 4-dimensional data, but we can't really plot all 4 dimensions at the same time in a very straightforward way. So often it's useful to do a pairwise plot of the two. So here we're plotting sepal length versus sepal width. And we can see that there's some sort of relationship here, right? The sepal length and width kind of cluster this Setosa species together. So looking at this, we might guess that you could do something in an automated fashion. You could do some automated classification here. So I'm going to skip over this quick exercise, but if you start looking at different combinations of features, it's possible to get an even better separation there, but we'll see that. So scikit-learn, as you're playing around with these algorithms, it has a lot of different data available, and you can see these in the data sets, scikit-learn.datasets.load_ and scikit-learn.datasets.fetch_, different data sets you can do. So for example, if you use IPython's tab completion, we can see that there's 20 newsgroups data. This is some text data you can play with. California housing data, like I was talking about, predicting housing prices. There's faces data. There's these species geographical distributions. So if you go online and look at different scikit-learn tutorials, there are a number of different data sets available. And you can see some examples on those. So we have... I have a question about the output. Yeah. You've got one output, either 0, 1, or 2. Mm-hmm. You also structured where you had 3 outputs that were just binary, 0 or 1. So there are species that affect the way models behave or not. Yeah, so the question was, I was talking about outputs with 0, 1, and 2. Other situations, there's just a binary output. And different models handle that better than others. So if you want to look, if you look up in the documentation, if you look at multi-class classification versus binary classification, there's some description about which algorithms handle those. But in general, we do have algorithms that handle both those situations. So we're running up against the break, and I just want to I want to show you a little case study. I'm going to skip ahead here just to motivate this a little more. How you might use machine learning in practice. So I'm in this second notebook here, and I'm going to just import. Actually, I'm going to run all in this notebook, and I'm going to scroll down to the bottom here where there is somewhere. Yeah, this quick application, optical character recognition. So just before we go to the break, I want to give you a little bit to chew on to see how this stuff that I was talking about, that's very basic in the beginning, can be built on top of itself to make things make some really interesting applications. So we talked about the different data sets that there are in scikit-learn. Here we're going to load the digits data set. So what this is it's a data set of handwritten digits. It's a bunch of, you can see the images here are an array of shapes 1797 by 8 by 8. So what this is it's about 1,800 little 8 by 8 snapshots, 8 by 8 thumbnails of handwritten digits that were scanned and then put into a normal pixel grid. So if we plot these, we can see what these look like. So each of these images are 64 pixels, and you can kind of recognize by eye what digits these are. So they're the digits 0 through 9. And the question is, can we use this data to build a classifier in scikit-learn that will automatically recognize a handwritten digit when it sees it? So as we talked about, the first thing we need to do is get our data in the shape of a number of samples by number of features array. So these images are 1797 by 8 by 8. One way we can think about this data, as I was saying with the irises, is we can actually look pixel by pixel and treat each pixel as its own feature. So here we have 8 by 8 pixels, so that means there's 64 features describing each object. And if we look at the digits.data, we can see that this is exactly what's going on here. We have a 1797 by 64 array. So each row of this matrix gives us the 64 pixel values that describe that digit. And then in the target, we have the numbers 0 through 9 that just tell us about what the value is of this data. So let's first take a look at, yeah, question. Mm-hmm.
They said, you can skip everything here, just learn Torch or CUDA or TensorFlow. You don't have to learn anything else. Is that oversimplification or that is true?
Yeah. So he mentioned he was in a deep learning tutorial, and they mentioned that you don't have to learn any of this. You can skip it all and just use TensorFlow. I would say maybe in practice that could work, but I think it's. I would be worried about recommending that without going through the background of what's going on under the hood. Like TensorFlow is kind of this magic black box, and it might work sometimes and it might not. And when it doesn't work, if you don't have a good idea about what's going on under the hood, it's hard to know how to debug it. So, but maybe it's magic enough that you don't have to understand it. Yeah. No, scikit-learn doesn't have any deep learning, but there's some interesting Python libraries that are similar to scikit-learn that have some deep learning applications. Yeah. So one way you can move forward when you're looking at data like this is to do some sort of dimensionality reduction. So scikit-learn has some dimensionality reduction routines, and what this will do is it'll allow us to take a look at our data and project it down into 2 dimensions rather than 64 dimensions. So now we can plot this data and see the relationships between our points. And when you look at this projected version of the digits data, we see something interesting in the relationships between the points, right? If you look at the black points there, those are the zeros. And the zeros kind of blend into the yellow points, which are the 6s. And so that gives you some intuition about what's going on here in these points. You can kind of imagine how you might morph a 0 to turn it into a 6. You take a 0 that's a little disconnected at the top, and then eventually that turns into a 6, right? So this unsupervised learning application lets us kind of see these relationships between data points, and see that 0s are related to 6s, but 0s are not related to 1s in the purple over there. So we look at this and we can tell that our data set has some sort of fidelity. It has some sort of way to capture meaningful information about the underlying data. So the features that we have here are meaningful, and we can see this in this sort of nonlinear projection. Now we can think about doing a classification task. So the first thing we're going to do is split the data into a training sample and a testing sample. So the training sample is what we're going to be able to use to train the model. The testing sample is what we're going to use to see how the model performs. And if we train a logistic regression, we take the scikit-learn estimator and we make a classifier, we train it on the training data, and then we predict on the data it hasn't seen before. We can get a prediction, and we can see that our algorithm is predicting this with 95% accuracy.
Do we have validation?
Yeah, there are validation routines in here as well. That's one thing that I want to get into after the break, but I just want to show you real quick what can be done with scikit-learn here. So if we can take a look at the confusion matrix. This will tell us, for example, that an 8 here was misclassified as a 1. We can show the confusion matrix and see this. So this shows us the predicted value versus the true value, and we can see that most of them are correct, but there's a few that are a little bit off. And finally, another thing we can look at is the data, the little thumbnails themselves. We can see that, for example, this 4, our algorithm predicted it was a 4, but this thing right here, which is apparently a digit, our algorithm called it an 8, but it's labeled something else in the data set. And this gives us a little bit of intuition about how the model is failing and where the model is going right. So you can see there, but just in a few lines of code, a few lines of scikit-learn right here, we've taken that input data and we've trained a model that, given a new image, can predict what that image label is. And right now we're going to take a afternoon coffee break, but after the break what I want to do is dive a little more into this and look at some of these things that I glossed over here, some of this API, some of the train test split, the fitting and the predicting and all this stuff, and give you an idea of how you can use this sort of thing on your own data in order to accurately predict things like handwritten digits or anything else that you're going to work with. So let's take a break now and come back here at 3:30, and we'll continue on with that. Thanks. All right. Why don't we start up again? So in this afternoon part of the session, I hope the first part wasn't too quick. I just wanted to give you an overview of the kind of things that we're going to dig into a little more this afternoon. This afternoon, I want to go through this notebook in detail, the basic principles of machine learning. So this is where we're going to talk about a little more in depth what classification and regression mean, what supervised and unsupervised learning mean, and then look more in depth as well at how to implement these things in scikit-learn with the scikit-learn estimator API. And once we do that, that kind of gives you the basis on which you can build some more knowledge about machine learning approaches and different techniques that are available. And from there, I want to jump into some of these more in-depth things on different algorithms that you might find useful in your own work. So I'm going to hopefully have time to get to support vector machines and random forests, because these, in my mind, are kind of the two most important supervised learning techniques. And then if we have the time, we'll also get into principal component analysis, which is a dimensionality reduction technique. and k-means, which is a clustering technique. And we're most likely not going to have time to get into these last few notebooks here. So I'd recommend, if you find this interesting, you can dig in yourself and read those. I tried to make them complete enough so that they can stand alone, so you can read through them yourself as a tutorial. So let's jump back into this basic principles here and start from the beginning. I'm going to toggle the header and toggle the toolbar to make this full screen. So basic principles of machine learning. We saw before how the simplest versions of a machine learning problem, where we're building an algorithm that can predict based on data that it's seen some labels for data that it's not seen. And the way this happens in scikit-learn is with an interface called the estimator object. So in scikit-learn, every single model that you want to fit, every machine learning model, is its own class. And every time you want to fit a model, you take this class, this kind of object-oriented programming class, and you instantiate it, and then you can start fitting it to data. So as a quick example, let's take a look at the linear regression model. So if you wanted to fit a line to data, you have this linear regression model, and you can import the model. And the first thing we're going to do is instantiate that model. We're going to ask scikit-learn for an instance of this model. And the model instantiation, one of the things that confused me at first about this API design, but what I've grown to love, is the fact that when you instantiate this model, it doesn't know anything about the data yet. So this is like, you can think of this as a blank slate. It's a model that says, I want to fit a line to some data, and you just haven't given it the data yet. And when you have this sort of model, you can inspect it and you can see what's going on with this. So this is a linear regression model where we are going to fit the intercept, and we're going to do n jobs equals 1. So this is n jobs tells you if you want to parallelize it, you can set it up to more than one job. And we're going to normalize the data before we go in. So this is like, you can think of the model as a recipe for what you're going to do when it finally sees data. Okay, now what we'd like to do is fit some data to the model. So let's create some really quick, some simple data. We're going to do x, and a range from 0, a range of 10 means this is the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Y is going to be 2 times those x values plus 1. So we have a straight line. And if we print those out, and plot them, we see the data right here. So this is the x values and the y values, 2 times x plus 1. So if you recall when we were talking about the form of data in scikit-learn, we need the data to be in a 2-dimensional matrix, a number of samples. The number of rows is the number of samples, and the number of columns is the number of features. Here, this x data is 1-dimensional, so we have 1 feature, and we have 10 samples. So we need to reform this data into basically a column vector. And if you're familiar with NumPy, one way you can do this is to use this new axis framework. So colon says, stick the old axis here, and then add a new axis of 1s. And what we get out is our column vector. So now our x is in this nice number of samples by number of features form. And finally, once we have the data in the right form, we can apply our model to it. So we're going to fit our model to this data. And to do that, you call the fit method on the model. And so we call the fit method, and what's returned is this model now that is fit to the data. And we can see all the parameters we saw above. And now if you're curious what happened with that model when you fit, if we look at if we use IPython's tab completion to see what's here, anytime you fit a model in scikit-learn, it will define some parameters that end with an underscore. And when those parameters that end with the underscore are ones that depend on the data, that were basically created by the data. So we have coefficients, we have the intercept, we have the rank, we have the residues, and singular. So these are all the things that were fit by the model when it looked at the data. And we can look at 2 of these. In this case, the coefficient is 2, and the intercept is 1. And you might think, you recognize these numbers because when we created this data up here, we said that the slope would be 2 and the intercept would be 1. So essentially what we've done is we've used scikit-learn to fit a straight line to this data and find out that the slope of our data was 2 and the intercept was 1. And then if you want to look at some of these other ones, we can see, for example, the residual errors around the fit. And we see that because this data is a perfect line, these residual errors are really small, 10 to the minus 31 or so, which is basically machine precision. Yeah? That's a great question. So the question was, how do you see the p-value for this? One thing to know about scikit-learn, and this kind of comes down to a larger divide in the statistics and machine learning community, is in machine learning, so there's a division between machine learning and statistical modeling. And statistical modeling, people tend to worry about things like the coefficients and the intercepts and the p-values and how accurate you are on how accurate your estimate of the slope is and things like this. On the machine learning side of things, people tend not to worry about the actual model parameters themselves, but instead worry about what the model tells you. So in scikit-learn, because scikit-learn falls on the machine learning side of that divide, you're not going to find things like uncertainties in model parameters. Most of that sort of work is done via a data-driven approach using cross-validation and things like that. So if you're coming from a statistical modeling background, there are parts of scikit-learn that might leave you wanting more. But that just comes from the fact that it's in this machine learning context. Hopefully that answers your question. So that's a long way to say you can't get them. Yeah. Yeah, you can calculate it by hand. If you're interested in p-values and those sort of classical statistical modeling things, you can look at the stats models package in Python, and that does some good things. Yeah.
Quick question on the model coefficients. You just have one coefficient in there, which is simple.
Mm-hmm.
Go back to the iris example, and you had that where you had 4 or 5 coefficients. I've noticed in this it just gives you an array, but does not label what coefficient it is. Is there a way to put the label on an array?
Yeah.
I'm stuck in the stats model type of.
Yeah, that's another good question. So he mentioned that if you have multiple columns, these coefficients aren't labeled, and it's hard to interpret them. And he asked if there's a way to get a label on those, and the answer is no, because usually these coefficients are treated as kind of an internal piece of the model and not something that the user is expected to really look at in a machine learning context. And if you want that sort of, I would say that falls more in the statistical modeling framework. And if you want that, there are other libraries that are better for that. For a linear model, it may seem a little bit silly to skip over that because you can compute those pretty easily. But if you think about generalizing the linear model to more complicated things like a random forest classifier where you might have 1,000 different trees and each of those trees has 1,000 different nodes, you're not going to want to compute detailed statistics about the split values of each of those million nodes. What you're interested in is how well your algorithm predicts on the data. So machine learning tends to treat statistical methods as a black box where you get inputs and outputs, and you figure out how good it is based on those alone. So it's kind of an interesting. There's a great article on this. Bryman, what's it called? Two Cultures. Yeah. There's this, if you want to read more about this, there's this article called Statistical Modeling, the Two Cultures by Leo Bryman. That's a horrible webpage. I'll stick with Google. Yeah, so read that, and he goes into detail. This was written 15 years ago or so, and he goes into detail on these two different cultures within statistics and machine learning versus statistical modeling and things like that. It's actually a quite interesting read. That was a fun digression. All right, so if we can move on. So this is the basic scikit-learn estimator interface, and the pieces that I want you to remember are that any model in scikit-learn, any type of estimator is a Python class. You instantiate that class to decide on what sort of hyperparameters you want, what sort of model you want to fit. Here's a normalized linear regression, for example. And then when you finally fit that model to the data, you call the fit method. And then there are these underscore things that are internal to the model that it creates for you. And then you can move on from there. So that's the basic estimator interface in scikit-learn, and we'll go on from there. So within that estimator interface, there are a couple different flavors of machine learning that you can do. So the one that you've probably come across most often is what's known as supervised learning. And supervised learning is maybe a little bit easier to wrap your head around. It's the kind of thing where you say, I have data, and I want to build something that can predict, that can be predictive for new data. So in my field, for example, in astronomy, you might have, say, given a multicolor image of an object through a telescope, determine whether that object is a star, a quasar, or a galaxy. You know, we want to classify things, and the way we do this is we have a training set with labeled objects, and then we have a test set that's unlabeled, and we can figure out the label for those. Other supervised learning things, given a photograph of a person, identify who the person is in the photo. Or given a list of movies that someone has watched and their personal ratings, recommend another list of movies that they would like. So this is the key here is that we have labeled data that we're trying to predict. We're trying to predict features about new data that we don't have labels for. So let's go into a classification example in a little more detail. Now that we know this scikit-learn API, we can go back to our iris data. And we're going to get the X array and the Y, the target array. We're going to take our model. In this case, we're going to do a k-neighbors classifier. It doesn't really matter at this point what this does. I just want you to see the algorithm itself. I want you to see the API itself. And we're going to say we want a k-neighbors classifier with 5 neighbors. We'll fit that to our data. And then finally, what we're going to do is with supervised methods, what we can do is call this predict method. And given a new set of data, what that predict method will do will tell us what label the algorithm thinks this is. So in this case, if we find an iris with a 3 by 5 centimeter sepal and a 4 by 2 centimeter petal, then our algorithm thinks that this iris is the versicolor species. So we've built this all in a few lines of code, and remember what we're doing here is we're instantiating the model, fitting it to data, and then predicting on new data. And depending on the model, you can also do things like probabilistic predictions. This predict underscore proba is a probabilistic prediction that says this has a 0% chance of being the first species, 80% chance of the second species, and 20% chance of the third species. So these are the kind of things you can do with supervised algorithms. And I created a little figure here that kind of lets us see a little bit what's going on in this algorithm. We have the sepal length by the sepal width here, and these are the labels for them. And we can see where, as a function of the sepal length and sepal width, where our algorithm might predict different species. And you can see that our algorithm is not exactly perfect, right? There's this blue point sitting out here that would be misclassified as a green point. And there's a green point over here that would be misclassified as a blue point. So there's some degree of mixing between these two species, but our red points there are pretty well classified. So that's one way you can visualize things. So this right here, this cell right here, I want you to see as the example of how you do a supervised learning problem in scikit-learn. And what I'd like you to do now as a quick exercise, there's this other estimator called the support vector classifier, SVC. What I'd like you to do is to get a prediction for this point right here, this 3542. Figure out what the SVC tells you that point should be. What species is that according to the SVC model? And you should, with the API design of scikit-learn, you should be able to just kind of drop this SVC in to that above code and get the result pretty quickly. So take a few minutes and try that out just to get your fingers on keyboards a little bit. Okay, so I ran through this myself. Hopefully you had a chance to look at it yourself. So you can, just as we did above, you can instantiate this model. And with the support vector classifier, you can see that it's a much more complicated model. There are a lot of little tuning parameters that you can do, like even things as detailed as the cache size for the calculation. But just as above, all of that stuff has default values that it'll use. We can fit the model to the data, to the x and y. And then we'll see inside the model that there are all these fit parameters. And in this case, like if we look at the dual coefficients here, you can see that the support vector classifier is much more complicated than the linear model. It's doing a lot of things under the hood that you might not necessarily understand. But fortunately, we don't have to worry about those coefficients. All we're interested in is what's going to happen if we call model.predict on this. And in this case, if we call model.predict, we get that this model thinks this iris is the Virginica species. So the support vector classifier and the k-nearest neighbors classifier gave different results. And this generally is something that happens if you apply different algorithms to your data. So this is why it's really important to figure out what the right algorithm is for the problem that you're working on. And deeper than that, you have to figure out what settings of these different parameters within your algorithm are optimal for the data that you have. And that's something that's done generally in scikit-learn and in machine learning in general via this cross-validation idea. So we're not going to get into that in detail today, but I do have a notebook down at the bottom on validation that if you're interested in reading more about that, you can dig in there. And what cross-validation is, or what validation is essentially you use the data set itself to tune the model. So you fit the model on half the data, and you hold out the other half, and then you see how it performs. And then you tweak your model a little bit, see how it performs, tweak the model a bit more, see how it performs. And you do that until you find a model that performs optimally on the data set that you have. So for that, when you do the cross-validation, you don't have to actually worry about what all these model coefficients mean and what the uncertainty is on them and things like that. And that's where this distinction between statistical modeling and machine learning comes in. So machine learning tends to use these really opaque black box models that you can't reason statistically about very easily. So instead, we do empirical tests of how well the model is doing. Yeah? Mm-hmm. Yep. Yeah. So the question was, if you have a small data set, sometimes you might be worried that splitting it makes it too small to really be useful, or that if you split it the wrong way, you might have heterogeneous splits that would not perform well. The usual way to get around that is to use something called cross-validation. So for example, you could imagine, let's say you have 100 objects and you want to see how well your model is doing. You could train on 99 of them and leave out just one, and then see how well you fit that one. And then you leave out the next one and you train on the other 99. And then you leave out the next one and you train on those 99. So then what you have is you have 100, you've trained your model 100 times on almost all the data. And each time you get an estimate of how well your model is doing. So that's a scheme called leave one out cross-validation. And there are other types of cross-validation that you can do as well. But generally, if with small data sets or even with larger data sets, something like that is what's used in practice. And then you also don't, in that case, you don't get bitten by the heterogeneity because you're basically using every point as a training point and as a test point. Yeah, that's a good question. So he said, how do you plot the SVC result like in something like this? It turns out this is why I hid this code, because it's not especially easy to do. So it's several lines of creating grids and then doing something, reshaping it, and then putting it in a p-color mesh on matplotlib. So it's not particularly easy, but if you dig around in matplotlib and NumPy a little bit, then you can figure out how to make a plot like this. Yeah. So this sort of plot is useful for toy data sets, just to give an intuition for what's going on. But as you get to more and more complicated data sets where you have many dimensions, it's harder to visualize things this way. I mainly put that there if you finish early, because sometimes there are like pros or ninjas in here that just finish everything really quickly. Yeah. Yeah, that's a good question. So he said, I mentioned that you shouldn't worry about the internal parameters, but he asked, when your model's not performing well, should you start worrying about the internal parameters? And I'd say in practice, it's not exactly like that. In practice, when your model's not performing well, it's better to rely on an intuition for what the model's actually doing, which is reflected in those parameters, rather than worry about the numerical values of these parameters themselves. And when we get past this introduction notebook, what I'm hoping to do in the last half hour or so is to give you some basics of that intuition of these algorithms and how you should think about them. So let's go on to the quick regression example. We saw earlier the linear regression for fitting a perfect straight line. This time we're going to add a little bit of noise to the data. So here's our x value, which is similar to before. The y is going to be 3x plus 2, but we're also going to add this random noise and take a look at what it looks like. So here's some data that there's maybe a relationship between x and y, but it's harder to see the exact relationship. But let's take a look at using scikit-learn, using this API we've been looking at to fit a linear regression. So we start by computing a linear regression. We start by instantiating this linear regression object. Then we fit the x and y data. And now we want to figure out some values to predict. So here, let's take regularly spaced values between 0 and 1. And we'll predict on those, and we get out what the y value is. And now we can plot the squeeze, which makes it one-dimensional, and xfit.squeeze, which makes it one-dimensional. And we see the result here. So here's our nice linear regression of this data. The blue is the input points, and the green is those predicted points using the model. And you can see that here, in this case, the linear regression is not going to perform very well. This is a very highly biased model. That means that the model doesn't have enough flexibility to actually account for what's going on in the data. So this is a place where the model that you're using is actually a problem. There's no way that you can draw a better line to this data that will actually fit it in a better manner, right? So instead of a linear regression, let's take the same code here. I'm just going to copy all this. And let's go down here and let's fit a random forest model. So I'm going to paste the code there. And instead of linear regression, let's just drop in random forest regressor. So I'll talk about what a random forest does later. But for right now, you can just think of a random forest as kind of a very flexible non-parametric model. So we've done everything the same, except we've changed this little expression right here. And now we get something that it's kind of an interesting model, and we see that it fits our input data much better. It gets in the sense of getting much closer to the input points. But there's still a question of, is this a good model, right? Or is this overfitting the data? Is this getting too close to the points and just reflecting the noise rather than the underlying signal we're looking for? So this is kind of a trade-off between the high bias model that doesn't have enough flexibility and a high variance model that maybe has too much flexibility. And again, I want to emphasize here the API. We're interested in random forest, so we import this estimator. We instantiate it. We call fit to fit it to data. We call predict to get the predicted values on new data, and then we can do what we want with the new data to evaluate it. So one thing that's interesting to explore here is that in the random forest regressor, there are a number of different hyperparameters. All these different things, the n estimators, the criterion, the max depth, the min samples split, min samples leaf, all of these are things that will affect the final fit. And what I want you to do right now is just explore a little bit, try going back to this code and changing some of these values of the hyperparameters in here, and just see visually what happens to the fit. How can you make the model simpler? How can you make the model more complex? And just get a feeling for some of the variation that can happen as you tweak those parameters. So I'll give you a few minutes to work on that. And so what you'll find as you play around with these things is that different models respond in different ways to these hyperparameters. And for example, here in the random forest, the maximum depth and the number of estimators really, really matter. So if we set these both to high numbers, 200 and 200 maybe, we get this. We get something that really responds to each individual data point. But if we set these to low numbers, say let's do 2 and 2, we get something that's not as responsive, and we can go even lower. Let's do 1 and 1. So this is a incredibly simple model of our data when we have a low maximum depth and a low number of estimators. So this gives you an idea of how random forest can allow you to adjust the complexity of the model just by raising and lowering these numbers here. And this is something that's really key when you're using machine learning in practice, is figuring out how to tune that model complexity so you're somewhere between this model, which is really biased, doesn't have enough flexibility to fit the data, and maybe this model right here, which could be overfitting the data. It's adjusting a little bit too much to all the noise in the data. So that was supervised learning. Any questions on supervised learning before I move on to talking about unsupervised learning? So just, yeah.
I mean, you pointed out that you get this danger overfitting if you play with these parameters.
Mm-hmm.
Are there sensible defaults to use regularization to avoid that, or is that like this is bare metal and you have to do that yourself?
Yeah, there's some of the algorithms. Okay, so the question was, I talked about how tweaking these is important, and you need to make them. You need to find the nice medium ground. But is there an automatic way to do that via regularization or something like that? There are models. Yeah, there are models that have regularization built in, but you can think of the regularization as another tuning parameter, right? You make the regularization really high, and it drives it to a very biased model. Very low, it drives it to a complicated model. So in general, the way that you find this nice medium ground is to do validation or cross-validation on your model. And pretty much every estimator will have these sorts of trade-offs built into it in its tuning knobs.